Okay, YouTube, in this last video we're going to be looking at what we call an infinite geometric series, which is basically the sum of all infinitely many terms of an entire geometric series, or a sequence, pardon me. So basically, if you can imagine, a sequence here, if we were to say the sum of some rule here, and we're going to assume that it's geometric here, I say start at the first term, but I don't want you to ever stop. And so basically we'd say, it's A1 plus A2 plus A3 plus, and we would go on forever and ever. We would even go out to the nth term and beyond. We would just go on indefinitely. And so if we were to add up all of these terms here, what would you suspect that you would get? And so, and a lot of times, I get this answer, well, you get infinity because you're adding together infinitely many numbers, you should get infinity. But this weird thing happens when you were to add up geometric sequences where the r value that you're multiplying by is somewhere between -1 and 1. That is to say, if I were to say take like 4 times a half indefinitely. This was, some random rule that I made up here. But basically what I want you to notice is that r, is a half. And, that's certainly between -1 and 1. What would happen if you were to take something times a half, times a half, times a half, times a half, times a half? Basically, something like this, I would get my first term as 4, second term is 2, next term is 1, next one is a half, next a fourth, an eighth, a 16th, and this would just continue to go on forever and ever. If I were to add these up, I get 6, 7, 7.5, 7 3/4, 7 7/8, 7 As a matter of fact, I would get 7 in after a while, let's see, 15/16, 31 30 I would get 7 in 63 Basically, it would start to get really close to 8 as I add these up. And the thing is here, there's infinitely many terms to this. So as the thing you are adding on, let's put it this way, as the thing you're adding on is getting smaller and smaller and smaller and smaller and smaller, then you can actually get a finite sum from an infinite sum that you're doing, a finite value from an infinite sum. That is to say that infinitely many things can add up to a thing that is actually countable. So taking a look at the sum of an infinite geometric series, I'm going to read through this first and then kind of take a look at this diagram over here to reiterate these facts. We say if r, if your common ratio is just what we're going to write here, a proper fraction. Proper fraction. The bottom of the fraction is bigger than the top, so your number that you multiply it by is going to get smaller. We say then the sum of the infinite geometric sum, okay, series, okay, everything, all the terms here. Don't ever stop, just keep going. We say in which a1 is our first term, so we have our a1 here, and then the common ratio is our r. So we're adding up all these terms of this geometric thing. But the sum of all infinitely many of them is given as this, so long as r is a proper fraction. You can do this. And so what I want to point out here is this. In comparison and in contrast with what we saw for a finite geometric sum, then what we get is this. You see these two formulas here. They're very similar. It's the only difference here is that with your finite, you have a1 out in front. If we were to move it up front and get rid of this value here, you could see that it really just becomes our infinite sum here. And so that being said, really what this means is that we have some needs. And these needs are basically going to be these. If you want an infinite sum, we need a1, which is our first term. We're going to need to know our first term value. And then we're going to need to know r, which is our common ratio. Very good? Okay, so to reiterate the fact that we can add together infinitely many things and get a finite answer, let's go ahead and take a look at what we would get here. If I were to have an r value of, well, let's check this out. We'd say 1/4 divided by 1/2. And we would multiply by the reciprocal, so we would get 1/4 times 2/1, which is 2/4, which is a half. So our r value is a half here. That's certainly within the range that we've indicated between -1 and 1 here. It's a proper fraction. Since that's the case, then if you were to add these up, you would get a half. A half plus a fourth is 3/4. A half plus a fourth plus an eighth is 7/8. We'd get plus this one here would be 15/16. Plus another 32nd would be 31/32. So basically what this is getting really close to is 1, and you can see this basically illustrated here. The sum of the first, say, two terms would be a half plus a fourth, which would be 3/4 of this thing here. But a half plus a fourth plus an eighth would be 7/8 of the total pi, and then a half plus a fourth plus an eighth plus a 16th is 15/16 of the total pi. And as you add this up, you just really get really close to the entire thing, or a value of 1. So what we're going to do is we're going to use this formula a1 over 1 minus r to find an infinite sum. So I like these much better than finite geometric sums. We could just do this with a lot less calculator work. So looking at what we have here, we say find the sum of the infinite geometric series. Well, first of all, we're saying this is the sum of all infinitely many terms of whatever our rule is here. I'll say rule. And so I am interested in maybe knowing the rule of this. We'd say that our first term here times our ratio to the n minus 1. Our first term has a value of 3. Now the ratio, we're going to have to look for this. We say, what is our ratio here? What we typically do is we grab a term like our 2 and we divide it by the term before it. We say 2 and 3 are very convenient. We say our ratio is just 2/3 then. We must be taking this times 2/3 to get to the very next term every single time. And so since that's the case, our R value is indeed 2/3. And we need to know that here. So we say 2/3 n minus 1. So basically we're finding the infinite sum of 3 times, in parentheses, 2/3 to the n minus 1. And we basically just write this as S. So all that being said, we're going to say we just take our first term over 1 minus r. So our first term in this case has a value of 3. We can see that here. Now our r value is 2/3, and I'm going to recommend highly that you do this in fractions. So 1 minus 2/3 is really 3/3 minus 2/3. I only say that because we want to get an exact value on our answer here. So this would be 3 over 1/3, which multiplying by the reciprocal will be 3 times 3 over 1, which comes out to be a sum of 9. So if we were to add up all infinitely many terms of this particular sequence, we would say we would get a sum that is finite in value, and this is the sum of all terms of our geometric sequence. We call the sum of the terms of a sequence our series. Cheers.